Our title today is Galvanic Cells. We have 2 more days of notes left. That's all. This one and tomorrow, and that's it, people. So if you're one of those nostalgia people, you should probably start feeling sad because we're almost done. All right. So a battery is an example of a galvanic cell. So to begin this, oxidation-reduction reactions involve a transfer of electrons, and we know that. Leo the lion says grr. If you're losing electrons, you're being oxidized. Gaining electrons are being, that would be the element that's being reduced. Okay, redox reactions can be broken down into half reactions. So now this is something new. This is something that we have not seen yet. So for instance, let's look at a typical redox reaction, which we've looked at lots and lots and lots and lots. So all I'm going to do right now is write a net ionic. So let's say that we've got some zinc solid, and it's reacting with some copper 2 ion. Okay, and that's going to give us some zinc ion plus solid copper. Okay, now because we've gone over these so many times, over and over and over again, what's being oxidized? What is losing electrons? Zinc is going from having an oxidation state of 0 to positive 2, and so zinc is being oxidized, and copper is going from having an oxidation state of positive 2 to 0, elemental. And so grr, it's gaining electrons, it's being reduced. Okay, so what we're going to do now is we're going to write the half reaction for this. The 2 half reactions. Because always in redox reactions, we've got 2 half reactions. So I'm going to put it up here again. Zinc solid plus copper 2 is going to give us some zinc ion plus solid copper. Okay, so let's write the reduction half reaction. So we're going to say reduction half reaction. Grr, gaining electrons. So the reduction half reaction is going to involve the copper, and so it's going to be Cu2 plus how many electrons? 2. Make sure I'm not doing anything weird. Gives me copper. And we can also write an oxidation half reaction. Oxidation half reaction. And again, you guys, you've seen this so many times that these words should not be intimidating you whatsoever. And in the oxidation half reaction, we're going to have zinc going to zinc 2 plus what? 2 electrons. Okay. So, a reduction half reaction and an oxidation half reaction. Okay, where there's one, there's always the other, right? We can't have reduction going on without oxidation occurring simultaneously. Okay, so the question is, how can we harness work energy from this? Can we harness work energy from this? Well, Yes, as a matter of fact, we can. The key to getting usable energy out of a redox reaction, the key is to separate the oxidizing agent from the reducing agent, or separate what's being oxidized from what's being reduced, thus requiring the electron transfer. To occur through a wire. Okay, so essentially that copper 2 plus is going to pull those electrons away from the zinc. The copper 2 plus is going to pull those electrons away from the zinc. And if we can separate the copper 2 from the zinc, and we can get that copper to pull the electrons from the zinc over a wire, then we can get those electrons traveling through the wire to do work for us. And that's what a galvanic cell does. That's what a battery does. So let's draw a picture. Okay, so this device is called a galvanic cell. A device in which chemical energy is converted into electrical energy. Now, in order for this conversion to occur, we need that redox reaction to be spontaneous. We don't want to have to put work in order to get that redox reaction to go. That redox reaction has to be a spontaneous reaction for us to be able to get usable work energy out. Okay, so that means that galvanic cells have a delta G of what? Are they positive or negative? Delta G is always negative for a galvanic cell. It's always spontaneous. It will go on its own. Okay, so this is a reaction in which, a redox reaction in which the value of K, the equilibrium constant, lies far, 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 far to the right, and it's spontaneous. All right, so let's draw one. Let's make a galvanic. All right. So here's a beaker. Here's a beaker. Here's a strip of metal. Here is another strip of metal. And they are attached via this really lovely pink wire. We also have here I didn't need to make these things so far apart. This thing, which is a salt bridge. This is zinc metal. This is copper metal. I want to do this. We have a liquid. No. No. Done. Out. These are all in a solution. Okay, and then this side, on both sides, you guys, we've got sulfates. SO4 2 minus, SO4 2 minus. That's a 4. That's sulfate. That's not a 3. Okay, so we've got sulfate ion, both sides. Now, remember back to our half reaction. Copper is being reduced. So we also have inside this beaker to start copper plus ion, and we probably have a little bit of zinc 2 plus ion in here as well. So in this we'd have a solution, a little bit of zinc sulfate, and in this one we've got copper 2 sulfate. All right, so what we've got here is the copper that is going to do what? It is going to pull the electrons from this zinc metal. And so electrons are going to travel in this direction. They are going to go from the metal that is being oxidized, losing electrons, to the metal that is being reduced. Now, what it's actually going to do is, of course, it's this copper 2 plus that's got the pull on these electrons that are going to take the 2 electrons and actually plate, well, not really plate up, but deposit here on this copper metal. And what's happening over here is that this zinc metal is slowly being oxidized so that the amount of zinc ion in this solution is going to continuously get more concentrated. What will eventually happen to that zinc metal? It will eventually all disappear. What's going to end up happening to this copper metal? Well, the mass of it is going to get larger and larger and larger as copper 2 is able to take electrons, get reduced, and become solid copper. Okay, now what the heck is going on with this salt bridge? Well, if you remember from physics, that the only way a circuit can go for these electrons to actually be able to travel, this circuit has to be what? The circuit has to be complete. And so this salt bridge allows for the movement of sulfate ion. So sulfate ion will move, and that will allow the circuit to stay complete. Okay, now we have special names for these electrodes depending on what's happening at them. Are they being oxidized? Are they being reduced? An-ox, red cat, meaning that this zinc is oxidized, so this is the anode. So oxidation happens at the anode. Copper is reduced, and we say that the reduction occurs at the cathode. So this is the cathode, this is the anode. Okay, so electrons are pulled. Electrons are pulled from anode to cathode. Okay, now you guys, let's not be fooled. The anode is not always on the left side of the picture, and the cathode is on the right side of the picture. That is not the way that it occurs. Okay, sometimes it will be written opposite. So the only way that you can identify the anode from the cathode is that you have to know what's happening where. The cathode is being reduced, and the anode is being oxidized. And so if it was the other way around, if this was zinc and this was copper, the electrons would be traveling in that direction. Okay, and so now what can we do? Well, we could put a little light bulb in here, and get the flow of electrons to light the bulb. Or we could use it for all sorts of things, right? Okay, so this is the basic thing about a battery. This is the way batteries work, but clearly they're not sitting in beakers of solution, and I am not an engineer, so I don't know exactly what they look like on the inside of a dry cell. But you could look it up online and figure it out. Okay, there's one more thing that we need to say, and then we're going to be done. And that is, this pole is termed, so that means the pull of the electrons from the anode to the cathode. This pull is termed the cell potential. Or the electromotive force. The abbreviation is a really pretty E. What's the unit of the pull of electrons, do you think? How much voltage can you get from a particular galvanic cell? Well, that's going to completely depend on the value of K, right? That's going to depend upon the oxidation reduction reaction and how forward that thing is going to go. And keep in mind again, one more time, that for all galvanic cells, the delta G is always negative, meaning that the thing is spontaneous. It moves forward without any outside intervention. Okay, do you think that we can calculate electromotive force from given a particular redox reaction? Well, of course we can. And that's what we're going to do tomorrow for our very last day of